All right. Well, thank you all for coming this morning. This presentation is my comprehensive exam. It's a proposal for the research I plan to do for my dissertation, the diode-laser-based direct detection Doppler wind Lidar. In this presentation, I will describe my instrument and its purpose in atmospheric science. I will then talk about the work I've done so far and propose a plan for completing this research. To begin, I'll describe the purpose of Doppler wind lidars in atmospheric science. Weather forecasting is the idea that weather can be treated as an initial value problem. Given the current state of the atmosphere, the laws of physics can be used to predict a future state of the atmosphere. In atmospheric science, the wind field describes the motion of air masses, and therefore the transport of moisture, mass, momentum, and energy, and is a key parameter in every numerical weather prediction code. Wind speed and direction measurements are necessary to support weather forecasting and other fields within atmospheric science. These observations are so important that the European Space Agency recently spent over $500 million to put a wind speed measuring LiDAR on a satellite with the ADM AOLAS camera. These observations are especially important within the lower free troposphere and the planetary boundary layer, the lowest region of the atmosphere. This figure was taken from a paper on numerical weather prediction, and it shows some of the complicated atmospheric dynamics that characterize this region. These turbulent phenomena can be difficult to model, and any uncertainties in the model will propagate forward into uncertainties and errors in the forecast. Better observations of the wind speed in this region would help to advance meteorology and atmospheric science, which in turn would help society reap the benefit of advanced weather forecasting. That is better public safety and the mitigation and prevention of economic loss. There would also be benefits in various other sectors like agriculture, transportation, and air quality forecasting. Remote sensing instruments like radars and lidars can provide these observations. Doppler wind lidar stands out for its ability to continuous in clear atmospheric conditions. These instruments work by emitting light at some frequency into the atmosphere and detecting light at a different frequency that is Doppler shifted motion of atmospheric molecules and particles. Frequency shift, delta F, is the Doppler shift. That's the same Doppler shift that is responsible for the change in pitch of a siren as an ambulance rushes past a listener. It can also be at wind speed. Speed of the outgoing beam of light. A LiDAR that points vertically can observe vertical winds. To observe horizontal wind speed and direction, the beam would need to be steered to non-zero zenith angles. A particular challenge of Doppler wind LiDAR is operating within a two-component atmosphere. That is an atmosphere that contains aerosol particles and gaseous molecules. In this context, a gaseous molecule is a single molecule of one of the compounds that comprises air, like diatomic nitrogen and diatomic oxygen. A particle is a solid or liquid aerosol particle suspended in the air, like dust, smoke, or steam. This figure shows the total scattering spectrum from the atmosphere. The broad Gaussian shape on the bottom is the Caban spectrum, which is the molecular scattering spectrum. Molecules vibrate with a thermal velocity of about 300 meters per second, so the spectrum from them is Doppler broadened by about 2 gigahertz. Aerosols don't vibrate with thermal motion, so the spectrum scattered from aerosols is the exact same spectrum as the transmitted laser, and it appears like a sharp spike at the center of the molecular scattering spectrum. The intensity of the molecular scattering spectrum, which is the height on this graph, can be modeled. But without additional measurements, the intensity of aerosol scattering is unknown. At this point, it's convenient to define the backscatter ratio. which is the ratio of the total atmospheric scattering to the scattering that comes only from molecules, where beta in this equation is the backscatter coefficient for molecules and aerosols, respectively. A backscatter ratio of 1 would indicate in Bozeman, Montana, the backscatter ratio is 780 nanometers, ranges between 1.5 to 3.5 within the planetary boundary layer, and is nearly 1 in the free troposphere. Going back to the total scattering spectrum, a non-zero wind would cause a coherent shift of the entire spectrum. This figure now shows the Doppler shifted spectrum that would be caused by a 100 meter per second wind, where the unshifted spectrum is shown as the black dashed line. One point I would like to emphasize is that Doppler wind lidars have to detect tiny shifts. For example, a 1 meter per second wind would cause a wavelength shift of 5 femtometers. That's 5 times 10 to the negative 15th meters at 780 nanometers. So Doppler wind lidars have to be precisely controlled instruments for the wind speed measurement to work. There are 3 major techniques for retrieving the wind speed with the Doppler wind lidar. Filter technique, which can retrieve wind speeds from the scattering by aerosols and molecules. The interferometric technique, which can do wind speeds using aerosols or molecules, but not both simultaneously, unless you were to put 2 different interferometers in the same lidar receiver. And the heterodyne technique, which retrieves the wind speed from the scattering by aerosols, but only aerosols. So it can retrieve wind speeds in the aerosol-dense planetary boundary layer, but not above it into the free troposphere. I plan to build a filter Doppler wind lidar that uses an ancillary measurement of the backscatter ratio to retrieve wind speeds using the signal from aerosols and molecules with a greater receiver efficiency than other previous filter Doppler wind lidars, like the Twilight instrument at NASA or the OHP LiDAR in France. Before I describe the instrument I plan to build, I will describe our group's previous work. Our group has a history of building diode-based LiDARs called the micropulse differential absorption LiDAR. These are designed to profile the thermodynamics of the lower atmosphere. And they were developed by researchers at Montana State University and the National Center of Atmospheric Research. They utilize a cost-effective diode laser-based design. They are eye-safe with a Class 1M designation, and they have demonstrated long-term continuous operation. Their flexible architecture allows them to be adapted to profile water vapor, quantitative aerosol backscatter, and temperature profiles. I will adapt the MPD design to build a Doppler wind LiDAR. This measurement would enable a LiDAR that can measure thermodynamic and kinematic profiles from the same volume of air. My thesis will be on the first iteration of this Doppler wind LiDAR, which will focus on vertical winds, but it will provide a starting point for future horizontal wind speed and direction measurements. Using the MPD architecture makes it so that there are some additional design constraints on the Doppler wind LiDAR. The wavelength has to be between 700 and 1100 nanometers because the lasers and the tapered amplifiers that the MPD architecture uses are only commercially available at those wavelengths. The wavelength must be combined and separated from the other MPD wavelengths. We can't use the 770 temperature wavelength or the 828 water vapor wavelength. And thirdly, we must use a filter technique. The avalanche photodiodes in the MPD receiver are poorly suited for an interferometric technique, and matching the wavefront of a laser with the wavefront of an atmospheric backscatter signal with such a large telescope that we use in the MPD would be nearly impossible, so the heterodyne technique is out of the question. The diode-laser-based direct detection Doppler wind LiDAR was proposed in a modeling paper by Kevin Rapasky with me as a co-author. It will combine the double-edge wind LiDAR techniques to simultaneously measure vertical profiles of the vertical wind speed and the backscatter ratio. In this block diagram, the double-edge wind LiDAR is shown in green, and the high spectral resolution LiDAR is shown in red. The double-edge wind LiDAR will operate at 780 nanometers, leveraging laser stabilization to a spectral line of rubidium. And the high spectral resolution LiDAR will operate at 770 nanometers, and we'll use the potassium absorption vapor cell as the notch filter in the high spectral resolution technique. Both lasers will be configured in master oscillator power amplifier configurations, with the tapered amplifier acting as the amplifier. The beams will be combined with the dichroic beam combiner and transmitted to the atmosphere with a shared transceiver telescope, which increases optomechanical stability. The figure to the left is a block diagram of the double-edged Doppler wind lidar technique. Light collected by the telescope will be incident on a beam splitter, where half of the light is sent to etalon A and the other half is sent to etalon B. The blue dot dash and the red dotted lines indicate the transmission spectra of these two etalons. If you look at the figure to the right, the total atmospheric scattering spectrum with a 100 meter per second Doppler shift applied is shown on the same plot as the transmission spectra for the two etalons, where the shaded regions represent the amount of photons that reach the receiver. That reach the detectors. In this case, more photons are detected by detector B than detector A. The ratio of the signals at these two detectors can be used in the double-edged wind lidar equation to determine the Doppler frequency shift. I won't get into the details of this equation, but I want you to notice the backscatter ratio, boxed in red, and the Doppler frequency shift, shown in green. There are two unknowns in this equation. So to determine the Doppler frequency shift, and therefore the vertical wind velocity, you have to measure the backscatter ratio. We will do that with the high spectral resolution LiDAR technique. The block diagram of that technique is shown in the figure to the left, where light from the atmosphere is first incident on a beam splitter, and some of it continues unattenuated into the combined detector, which receives light from aerosol and molecular scattering, whereas the other half of it is reflected to a potassium cell, where the potassium cell transmission is shown as the red dotted line. If you look at the figure to the right, you can see that the photons that arrive at the molecular detector are only from molecular scattering and contain no aerosol scattering. The ratio of the signals in these two detectors can be combined in the high spectral resolution LiDAR equation to retrieve the backscatter ratio. Once again, I won't go into the weeds of this equation, but all of these quantities on the right side are known. So with the backscatter ratio measured, the Doppler frequency shift can be measured with the double-edged wind LiDAR technique and used to retrieve the vertical wind velocity. The instrument that I will build will be the same in concept as the one from Kevin's paper, but it will be different in implementation. Rather than combining two LiDAR techniques in one instrument, I'll use two instruments, one of which will be a double-edged Doppler wind LiDAR, and the other will be a high spectral resolution LiDAR. I'm doing this because we already have the high spectral resolution LiDAR. This block diagram shows the double-edged wind LiDAR that I will build. The laser will operate at 780 nanometers and will be stabilized to a rubidium cell using frequency modulation spectroscopy. It will be configured in a master oscillator power amplifier configuration, tapered amplifier acting as the collimating optics and an Axicon pair will convert the circular beam into the astigmatic beam into a annular beam, which will be transmitted to this telescope and transmitted to the atmosphere through a transceiver telescope. Light collected by the telescope will be coupled into a multi-mode fiber and taken to the receiver, where narrowband interference filters will remove the sky backgrounds and fused silica etalons will act as the edge filter. This instrument aligns with previous MPD designs with two exceptions. I will need to develop laser stabilization to rubidium, and I will also need to develop better temperature stabilization for the fused silica etalons. And I'll describe both of these subsystems in greater detail in the completed work section. This table shows some key parameters of the LiDAR instrument. I want to draw your attention to the low pulse energy of only 5 microjoules and the high pulse repetition rate of 10 kilohertz. This low pulse energy and high repetition rate enables eye-safe operation at the telescope exit aperture. That means I could stand above the telescope and stare directly down into the oncoming beam with no eye damage. Operating this low power means we need to use a large telescope. and I'm using one that is over 40 centimeters in diameter. Light collected by this telescope will be coupled into a multi-mode fiber, and the core of that multi-mode fiber will act as the entrance pupil for the receiver system, which will prevent any light from off-axis angles from entering the receiver. We have a very narrow field of view, only 115 microradians, which means that our geometric overlap function comes into full overlap at 3.5 kilometers in the atmosphere. That's a trade-off of the MPD system. That extended overlap means we get good signal in around 3 to 4 kilometers at the expense of getting less signal at lower altitudes. This is a block diagram of the instrument that already exists, the high spectral resolution LiDAR. And I won't go into this in detail. This is the instrument that I use for my master's research and the one that Owen is currently using for his Ph.D. research to retrieve temperature profiles. Know that it already exists and has already demonstrated reliable backscatter ratio retrievals at 770 nanometers. We the errors that we expected to see in this wind speed retrieval. We modeled the major expected error source and their contribution to the total wind speed retrieval error in the modeling paper, and found that the wind speed can be retrieved with an accuracy of 0.63 meters per second from 500 meters to 4 kilometers with a 5-minute averaging time and a 150 meter range resolution. With that accuracy, I believe that the diode-laser-based direct detection Doppler wind LiDAR can serve as a low-cost instrument that can profile wind speeds in the planetary boundary layer and the lower free troposphere, as well as a comparison of 3 technologies: direct detection Doppler wind LiDARs that other groups have created, my instrument, and commercially available heterodyne Doppler wind LiDARs. Heterodyne Doppler wind LiDARs can be bought with a price tag between $250,000 and $400,000, and they can precisely measure the wind speeds in the aerosol-dense planetary boundary layer, but they can't extend their measurement into the lower free troposphere. Other direct detection Doppler wind LiDARs can extend the measurement into the free troposphere, but these are expensive, sophisticated research instruments, and none have ever been developed into commercial product. The diode-laser-based direct detection Doppler wind LiDAR can also measure wind speeds in the planetary boundary layer and the lower free troposphere, and I estimate that the one I'm building costs about $100,000 in parts, so it could be made for a similar price point as the commercially available heterodyne Doppler wind LiDARs. I don't want you all to walk away from here thinking that my instrument is the best of both worlds, as the one I'm building requires a longer averaging time than the other 2 technologies to retrieve wind speeds with the same precision. Nevertheless, it will be a valuable instrument for providing direct detection wind measurements in a cost-effective package. My research can be summarized with 3 objectives. The first is to develop and demonstrate this instrument. The second is to develop technologies that advance diode laser-based LiDAR in general. And the third is to demonstrate scientific research capabilities with this instrument. And I will do that by observing the mixing height. The mixing height is the vertical extent of turbulent mixing, which means updrafts and downdrafts in the atmosphere, and is the height to which surface constituents like water vapor and aerosols and temperature become well mixed in the turbulent boundary layer. I will now transition into the work I've completed so far, and this can be split into 4 sections. Laser frequency stabilization, which is complete. Laser transmitter assembly, in progress. Eidolon temperature stabilization, which is nearly complete. And LiDAR receiver assembly, in progress. The laser frequency stabilization and the Eidolon temperature stabilization were the 2 new subsystems that I needed to create for this LiDAR to work. I stabilized my laser using frequency modulation spectroscopy to the saturated absorption spectrum of rubidium. Frequency modulation spectroscopy is a technique that can be used to measure the derivative of a transmission spectrum. Excuse me. In short, the error signal, which is the voltage output of the frequency modulation spectroscopy system, is proportional to the derivative of the transmission. Rubidium at room temperature is a vapor when it is kept at a low pressure. I use a glass cell full of low pressure rubidium for this stabilization. This is the transmission spectrum of that rubidium cell in a single pass configuration. If I set up a double pass configuration, we observe a pump probe effect, where these peaks riding on top of the transmission spectrum are the hyperfine transitions of rubidium. The Doppler broadened spectrum is about 2 gigahertz, but these hyperfine lines only have a line width of about 6 megahertz. If I then apply the frequency modulation spectroscopy technique, I can observe an error signal shown in red. Zooming in on these two peaks, we can see that the error signal has a zero voltage crossing. Wherever there is a peak in the transmission spectrum. These are the lock points of the laser stabilization system. The figure on the right is the control loop block diagram, where red lines indicate the optical paths and blue lines indicate the electrical wires. This is very similar to the familiar Pound-Reaver-Hall laser stabilization system. All the electronics are the same. The one exception is that I'm using the transmission spectrum of a rubidium cell rather than the reflected spectrum from a high-finesse Fabry-Perot cavity. One detail I would like to point out is that I'm applying my sidebands externally with an electro-optic modulator so that the spectrum I transmit to the atmosphere carries no sidebands. The electronics for the system are all commercially available, with the one exception being that I created a custom servo amplifier. To determine the stability of the stabilization loop, I stabilized two identical lasers to identical hyperfine transitions in the saturated absorption spectrum of rubidium. In a 48-hour experiment, the beat note had a stability of 97 kilohertz. That means that the relative stability of the two lasers was 97 kilohertz, indicating an absolute stability for a single laser of 69 kilohertz, which would cause wind speed error of 0.027 meters per second. The goal for this laser frequency stabilization was 500 kilohertz, and the system that I built has demonstrated stabilities on the order of 100 kilohertz for weeks at a time. This portion of the project can be considered complete. All the parts for the laser transmitter have been purchased, and the transmitter has been designed. This figure shows a block diagram of the system, and this figure shows a SolidWorks assembly drawing of what it will look like when completed. Right now, I'm using the laser to test the Eidolon temperature stability, but after I'm done with those tests, I'll be able to assemble this laser transmitter. This slide shows some photos of the components I've built so far. In the top left is the tapered amplifier assembly with collimated optics and a circular polarizer that acts as a quasi-isolator, preventing any retroreflections from beyond the circular polarizer to make its way back into the tapered amplifier. In the bottom left is an Axicon assembly, which converts the circular beam into an annular one. Bottom center is the TR assembly, which serves two functions: expanding the laser beam into the telescope and collecting light that has been collected by the telescope and focusing it into the multimode optical fiber. The figure on the right is a temperature-stabilized laser enclosure, which helps with laser frequency stability. The second new technology to develop was better temperature stabilization for the fused silica eidolons. Unlike other double-edged lidars, our system will use fused silica eidolons for filters. Most other double-edged lidars use a free space Fabry-Perot cavity with some sort of piezoelectric transducer that controls the spacing and an active lock to the laser wavelength. Fused silica eidolons are a thin cylinder of fused silica with reflective dielectric coatings on both faces. The Fabry-Pro cavity is inside the silica substrate. The figure to the right shows one next to a standard crown glass lens for a size reference. These fused silica eidolons are easy to use and they're optomechanically stable. But because there's no active piezoelectric control, the only thing that determines the frequency stability is the temperature stability. So there needs to be a much more precise thermal control for the system. In our case, we need the temperature stability to be less than 5 millikelvin. That's 5,000ths of a degree Celsius. This will be achieved using 2 layers of active temperature stabilization, where each layer is a loop containing a thermoelectric cooler, a thermistor, and a commercially available temperature controlling module. The figure to the right is a block diagram of the temperature stabilization system, where the second is suspended in a chamber at the center of the first stage. The photo on the right is the second stage. It is a copper insulated by rubber foam and a 3D printed jacket. The eidolon is embedded at the center of this copper block, and indium foil ensures good thermal contact between them. Anti-reflective coated windows surround the eidolon, preventing any free convecting air from touching the eidolon. The photo to the right in this slide is the first stage. It is essentially an insulated aluminum chamber that is actively temperature stabilized. It's surrounded by rubber foam insulation and a 3D printed jacket. If you look at the cross-section view on the far left, you can see the second stage suspended inside the chamber at the center of the first stage. It is attached to the lid of the chamber, which is made of acetyl plastic, Delrin. So there's no conductive heat path between the first and second stages. The heat sink for the second stage is fed through a hole in the lid of the first stage, which allows the second stage to use the ambient environment as a heat reservoir. It's attached using a rotating stage, and this allows there to be angular tuning of the angle of incidence between the laser and the eidolon, in addition to the temperature tuning. In short, the first stage provides a thermally stable environment for the second stage, which actively thermally stabilizes the eidolon. The temperature stability of this eidolon was tested by stabilizing the laser and tuning the eidolon so that the sideline of the transmission spectra was at the laser frequency. Any changes in temperature to the eidolon would cause a coherent shift of the entire spectrum to a higher, and that would cause a change in transmission through the eidolon. A power reference measurement was taken by splitting the laser before passing it through the eidolon. The best performance of this was a temperature stability of 1.15 millikelvin for 96 hours. This figure is a time series of that data, where the red dashed lines are the transmission levels that would be plus or minus 5 millikelvin from the mean of this time series. In this figure, I've changed the y-axis to the temperature change from the mean. This was the best performance, however. During these 4 days, the temperature of the room only changed by about 0.4 of a degree Celsius. In a normal day, the temperature of our lab changes by about 2 or 3 degrees Celsius. And on those days, the temperature stability isn't this good. In all conditions, however, I've observed temperature stabilities less than 2 millikelvin for 1 hour time periods and less than 10 millikelvin for 24-hour time periods. The 1 hour time period is the important figure here because we can apply a bias correction for normal Lidar operation to correct for temperature drifts on a time scale longer than 1 hour. And I'll talk about those bias corrections in greater detail in the research plan section. All the parts for the Lidar receiver has been bought and it has been designed. This figure shows a block diagram of the Lidar receiver. And this figure shows a SOLIDWORKS assembly drawing. Notice the temperature-stabilized Eidolon mounts interfacing with the rest of the receiver using the Thorlabs cage cube system. This is an exploded view which demonstrates the modular design. Right now, I have everything you see here completed, except I only have one temperature-stabilized Eidolon mount completed. I need to finish making the second one, and then I will be able to put this LiDAR receiver together. This is a photo that shows what the LiDAR receiver will look like, except I'm using an early prototype of the temperature-stabilized Eidolon mount. I updated the error analysis from Kevin's paper using the laser stability and the Eidolon temperature stability that I found through experimentation. And I found that with the new values, the accuracy is now 0.4 meters per second from 500 meters to 4 kilometers for a 5-minute integrating time and a 150-meter range resolution. I'm now going to propose a plan for completing this instrument and validating the measurement. This plan can be split into 3 phases: hardware assembly, software development, and testing, troubleshooting, and validation with mixing height retrievals. The first step of the first phase, is to assemble and align the laser transmitter. This shows what the laser transmitter will look like when completed. I will also need to take spectral purity measurements of the output of the tapered amplifier with an optical spectrum analyzer. And these figures show those measurements taken by the MPD group at the National Center for Atmospheric Research, which I plan to replicate. The figure to the left shows the spectrum of the tapered amplifier output in red, and the figure to the right is spectral purity measurements with respect to the seed power into the tapered amplifier and the current driving the tapered amplifier. I'm specifically looking for an effect called amplified spontaneous emission. Without a seed laser input, the tapered amplifier acts like an LED. When you put a seed laser into the tapered amplifier, most of the emission becomes stimulated, but there is still a small amount of this broadband LED emission, which is about 20 nanometers wide and not necessarily centered on the laser wavelength. This broadband amplified spontaneous emission will cause errors in the wind speed retrieval. It can be reduced to acceptable levels through tuning the seed power into the tapered amplifier, the current driving the tapered amplifier, and by properly aligning it. The second step of the first phase will be assembling and aligning the LiDAR receiver. This is what that will look like when completed. I will also need to characterize the transmission spectra of the 2 Eidolons. This figure is the transmission spectra from the wind LiDAR receiver from the Haute Provence Observatory in France. I will need to replicate this for my system. I will do this by scanning the laser wavelength over the transmission spectra, measuring the transmission at each point, and then fitting area functions to the measured data. Once the transmitter and the receiver are built, I will align them with the telescope in a roof port equipped laboratory on the 6th floor of Copley Hall. This image shows the cart that will next to the telescope, and this telescope will be beneath a roof port, which can be opened and allow transmission into the atmosphere. There's also this laboratory, which will allow horizontal propagation for the validation measurements, which I'll talk about more in a few slides. The second phase is software development. The instrument will be controlled by a LabVIEW program, and the high spectral resolution LiDAR already has a LabVIEW program running it, so I'll be able to reuse most of that code for this double-edge wind LiDAR, with a few small changes. This LabVIEW program will continuously collect data and store it as the netCDF files. It will control the temperature of the Eidolons, monitor whether or not the laser is stabilized, collect background photon counts, conduct calibration scans, which monitor long-term drifts in the Eidolon transmission, and measure biases so that they can be corrected for in the wind speed retrieval. I'll talk more about this calibration scan and the bias measurements in the next few slides. Starting with the calibration scans. To calibrate the ailerons, the tapered amplifier will be turned off and the laser will not be stabilized. A shutter will be closed at the focal point of the telescope. The laser light incident on the tapered amplifier will mostly be absorbed by that tapered amplifier, and a tiny amount of the diffuse reflection from the camera shutter will make its way back into the LiDAR receiver and reach the detectors at low enough count rates so as to not oversaturate the avalanche photodiodes. This figure shows a block diagram of where the shutter will be located in the system. The bias correction measurements will be very similar to the calibration scans, except the laser will remain stabilized. Going back to the aileron transmission spectra, the calibration scans will map out this, and those will be conducted about one. The bias correction measurements will only measure the transmission point. So the calibration scans will map out the entire spectra, and the bias measurements will detect how much these spectra have shifted coherently to a higher or lower frequency. And the bias measurements will be taken they'll be taken once per hour during normal operation. These measurements should only take about a minute to complete, and that means that the temperature of the ailerons only needs to remain stable between consecutive bias correction measurements. These measurements can be used in the vertical wind velocity retrieval to correct these spectra and correct for temperature drift in the ailerons. I will also need to write a retrieval program in MATLAB that takes the raw data and converts it to the vertical wind speed velocity. I will use the surface weather station to model the atmosphere and generate the Caban spectra, which is the molecular scattering spectra. The backscatter ratio will be provided from the high spectral resolution LiDAR. The data collected by the double-edge wind LiDAR will be corrected and fed into the vertical wind speed retrieval, along with the transmission curves measured by the calibration scans and the bias corrections measured by the bias measurements. The two outputs of the system will be a vertical wind speed and a vertical wind speed error estimate. The third phase will include troubleshooting, testing, and horizontal validation. It would be unusual if the LiDAR worked perfectly the first time I transmitted the beam to the atmosphere. So we've pre-allocated time to solve unknown issues. Once the wind speed is retrieved by the LiDAR and it appears realistic, meaning it looks like updrafts and downdrafts that we could expect in the lower atmosphere, I will move to horizontal validation. The horizontal validation measurements will be taken by propagating the beam horizontally out of the window of the laboratory to the east over Pete's Hill, 1.5 kilometers away from the instrument. I will then go over to Pete's Hill and use an anemometer, which an anemometer is a propeller-based probe that can measure wind speed and direction at a point, and use those anemometer measurements and compare them to the LiDAR retrieved wind speed measurements for a validation campaign. Once the measurements are validated, I will use the vertical wind speeds to retrieve the mixing height. And like I mentioned, the mixing height describes the height of turbulent mixing in the atmosphere. It's the height to which surface constituents and moisture and energy become well mixed into the atmosphere. It's a critical factor in numerical weather forecasting. The mixing height will be retrieved by observing the temporal variance of vertical wind velocity. The temporal variance will be high within the turbulent planetary boundary layer and low within the stratified free troposphere. So the mixing height can be found by locating a point which the vertical wind velocity falls below some threshold. These retrievals will be compared to the high spectral resolution LiDAR mixing height retrievals. These images show high spectral resolution LiDAR mixing height retrievals, where in these images, the y-axis is the altitude, the x-axis is a day of time, In the top plot, the color scale is the aerosol backscatter coefficient. And in the bottom plot, it's a cost function for my layer tracking algorithm. The black and white line is the mixing height, which I've labeled as the planetary boundary layer height in this figure. I have a high degree of confidence that if I can accurately retrieve the vertical wind velocity, I'll be able to find this mixing height. I already have a paper published on finding the mixing height using the high spectral resolution Lidar, and I know how to make these algorithms. Before I conclude, I'll give a list of publications I expect to come out of this research. The most important one will be the demonstration of the instrument with comparisons to the anemometer measurements. The second will be the design and demonstration of the temperature-stabilized eidolon enclosures. An eidolon enclosure can maintain the temperature stability of 2 millikelvin on an hour time scale will be of interest to researchers beyond the wind LiDAR community. The third is a demonstration of scientific research capabilities with the mixing height retrievals. And the fourth is a side project. I would like to use the micropulse differential absorption LiDAR operated by the National Center for Atmospheric Research. This is a water vapor profiling LiDAR during a recent field experiment to retrieve the mixing height. This is a continuation of work I did for a conference paper back in 2022. At the time of the conference, I only had access to a small data set of weather balloon comparisons, but with this field experiment, I now have access to a large data set. I've been holding off on working on this until I have the instrument put together. Once I have the instrument put together, I'll start working on these mixing height retrievals. And to conclude, a diode laser-based direct detection Doppler wind combines double-edge wind LiDAR and the high spectral resolution LiDAR techniques for simultaneously profiling vertical profiles of the wind speed and the backscatter ratio has been conceptualized. Two necessary subsystems for this instrument, laser frequency stabilization and eidolon temperature stabilization, have been developed, and work has commenced on assembling the laser transmitter and LiDAR receiver. A plan for assembling the instrument, developing the software, validating the measurements, and retrieving the mixing height has been proposed, and developing remote sensing instruments like this one is vital for advancing atmospheric science and weather forecasting. Finally, I'd like to acknowledge funding by the National Science Foundation. Thank you all for your attention. I'll now take any questions. Steve.
Correct me if I'm wrong. Wind speeds average to zero over time speed.
Yes.
About that at all over your
Right. So the question was, with a 5-minute integration time and the vertical wind speed averaging to zero over long enough time scales, what are we going to be able to see in the atmosphere? So I suppose I have two responses to that. The first is we probably won't be able to observe, well, with a 5-minute averaging time, we won't be able to observe updrafts and downdrafts in the lower atmosphere. We will be able to observe things like mountain waves and gravity waves, which we expect to see in Bozeman. However, if we go to the air analysis, we can see that the Poisson noise, which is the random noise caused by the integrating time, for 5 minutes is 0.33 meters per second. If we take that down to a minute, this Poisson noise will be increased by the square root of 5, which comes out to about 0.8 meters per second. So on the minute time scale, we'll be able to retrieve wind speeds on the order of with an errors on the order of 0.8 meters per second. So with that, we will be able to observe strong updrafts and downdrafts. Thirdly, we'll be able to observe vertical velocity variance, which won't demonstrate the momentary updraft or downdraft, but will demonstrate the average of the updrafts and downdrafts over some time series. We can do this by a technique called the autocovariance extrapolation technique, which can separate the real fluctuations due to updrafts and downdrafts from which are time correlated, to the randomly correlated Poisson noise.
Isn't going to be able to be crafted up. Data he's measured well with the
Right, and Kevin just mentioned that the standard weather forecasting models don't have such a high resolution fluid dynamic model to capture the single updrafts and downdrafts. And what I'm able to measure is on the order of the time scale of what the weather forecasting models have in their models. A question from Rob.
Yeah, can you hear me? Luke, can you hear me? I'm just going to try to ask a question. If you can't hear it, I'm sorry. Nice presentation for starters. The question is, it seems to me that the harder thing to do is to measure vertical winds versus horizontal. And your plan is to measure vertical winds first. First question is, did I catch that right? And the second one is, can you explain why you wouldn't flip that around and try to measure horizontal winds first?
Yes. Hey, Robert, are you able to hear me now?
I can hear you just fine. Yeah.
Okay. Yeah, so it's easier to measure horizontal winds because horizontal winds they have a greater magnitude. It's not easier to create a Lidar that can scan to those non-zero zenith angles. That would be not a trivial engineering problem to do that.
But you've planned to do it, right? So if I understand your plan correctly, you said we're going to measure vertical winds to see if we get reasonable updrafts and downdrafts, and then we will try a campaign with an anemometer. So
Yes.
that doesn't sound like a scanning system to me. That sounds like a mirror. So why don't you flip those? Because you're talking about orders of magnitude stronger winds in the horizontal than you are in the vertical.
Right. I think our plan is to measure these vertical winds to align the Lidar well, pointing vertically, and we'll be able to determine how well the Lidar is aligned by that might be a good idea, Robert. We may consider doing that.
Fair enough.
Can you hear me, Rob?
Can hear you just fine, Kevin. Yeah.
So if you think about the technology readiness level ladder, this proposal was put in to demonstrate that this technology is feasible with diode lasers. The cheapest and quickest way to demonstrate the feasibility is to use the already existing HSRLs in our roof-port facilities, which really mean pointing vertically, is the easiest way to start developing and demonstrating this technology. If we show we can do wind measurements vertically, then we can continue this research. With the next step would be adding some scanning capabilities to do horizontal measurements.
Yeah, I guess, Kevin, my point is that you don't need to scan it, but the vertical winds, let me actually ask Luke this question. What are the vertical winds you're expecting?
On the order of a few meters per second, like
a few meters per second?
The updrafts and downdrafts in the turbulent boundary layer should be about 1 meter per second on average, with stronger ones being 2 meters per second.
Okay.
They'll average to 0.
Yeah, I guess I'm not an expert at all, but my expectation was that vertical winds were centimeters per second, maybe tens of centimeters per second. Horizontal winds are, well stronger, but I will, I just want to say nice presentation, but I can also defer and I don't want to argue about it at the moment.
Right. And for that reason, that's right. I think because of our expected error here, the real dream of an instrument using this technology would be measuring these horizontal wind speeds. But to be able to demonstrate vertical wind speeds that average to 0 with this and vertical velocity variances with this will
Fair enough.
be readiness, which could then be developed into some sort of horizontal instrument. And some sort of horizontal point, we can do a vertical point easily with our facility, as well as one parallel to the ground directly out of the window. And we do plan to do both. Enough to demonstrate.
Other issue there may not be aware is there's a lot of issue with planetary boundary layer height retrievals. But that's an important measurement that a lot in this atmospheric science community want. And so providing vertical winds combined with the HSRL, combined with the water vapor, will allow Luke to expand his cost functions for his retrievals, and I think provide a much more accurate way of following the boundary layer. And so if he can demonstrate the vertical wind measurements, then I think a very straightforward science application from that comes from incorporating that in his cost functions for the planetary boundary layer height retrieval.
Fair enough.
For those of you who don't know Robert is a scientist at the National Center for Atmospheric Research, and he's been very valuable in coming up with advice for developing this instrument.
Clarification. The vertical.
The average over our time scales will be 0.
5 minutes though.
5 minutes, it will often be 0. 1 minute, it will be 0 in a stable atmosphere, but not so in a turbulent atmosphere. Erica. The question was, does the bias correction measurements ease the 5 millikelvin temperature requirement? It doesn't make the temperature stability requirement less than 5 millikelvin, but what it does is it makes it so that I only need to maintain that 5 millikelvin between consecutive bias correction measurements, which will be taken every hour. So rather than having to maintain 5 millikelvin for weeks at a time, which I found is incredibly difficult, I only need to do it for an hour at a time, which I already have completed.
Mostly asking because I've sat and I've been
Right. Right. I have considered what she mentioned was, since I'll have the open roof port, I'll have cold air from the roof flowing down into that room, which will make the temperature stability difficult. And yeah, I have considered that problem. I think that the Eidolon mounts are well enough insulated so that they'll be able to handle the influx of cold air. But you're right, that will make it more difficult. Oh, really?
But we're waiting for facilities to do that kind of stuff. Happen anywhere from 10 years out.
Okay. I just learned that there's plans to put a window on that roof port. No, that'll be a good thing.
Other questions from? Reconvene with just the committee. Robert, thanks for joining.
Yeah, thank you so much for joining, Robert.
Thank you for having me.
Cole, I saw you on here as well. You're gone.
Yeah, Robert, this is Joe. This is Joe Shaw saying hi. I'm glad to see you joining us. Thank you.
Robert on the committee.
Good luck, Luke. You're close to work.
Thank you, Robert. All right, I'll stop that recording.